We've all seen the pictures, ghostly tails stretching across the sky, dirty snowballs hurtling out of the darkness, messengers of chaos and change. Comets are supposed to be violent, unpredictable. They sublime, they crack, they burst apart under the sun's brutal glare. But there's a visitor from the outer dark whose story flips the script. An object that was supposed to put on the show of a decade, then quietly fell to pieces. The key to its secret isn't in its bright death, but in its slow, steady life. What does a 16-hour spin tell you about a comet? It tells you everything that matters. Comet C 2019 Y4, better known as Atlas, was an object from the Oort cloud, the solar system's deep freeze. This isn't a place you can visit. It's a gravitational boundary, a vast spherical shell of over 1 trillion icy bodies, leftovers from the birth of the planets, orbiting our sun at a distance that starts at 20,000 and extends to 100,000 astronomical units, nearly a light year away. These aren't asteroids, they are the pristine, unprocessed building blocks of planets kicked out of the inner solar system 4.5 billion years ago by the immense gravity of a young Jupiter and Saturn. They exist in two populations, an inner, donut-shaped region called the Hills Cloud, and the vast, spherical outer cloud. Atlas came from the outer cloud, a region where the sun's gravity is so weak that the pull of passing stars and the tide of the Milky Way itself can stir the pot. Out there, in the absolute cold and stillness, they drift for eons, undisturbed. A slight gravitational nudge can dislodge one of these relics and send it falling inward on a journey that takes millions of years. Atlas was one of these long-haul travelers, a true primordial object making its very first run into the furnace of the inner solar system. It was spotted on December 28, 2019 by the Asteroid Terrestrial Impact Last Alert System. Atlas isn't one telescope, it's a network. 4 half-meter telescopes, 2 in Hawaii on Haleakala and Mauna Loa, 1 in South Africa, 1 in Chile. They are designed to scan the entire visible night sky every 2 nights. The process is robotic, relentless. A telescope stares at a patch of sky, taking 4 15-second exposures. The software stacks them and subtracts any known stars or galaxies. It looks for anything left over, anything that moved. On that night, it was just a few faint pixels, a smudge that wasn't there on previous surveys. An automated alert went out, a new object, moving on a cometary path. It was given its designation, C 2019 Y4, the 4th comet discovered in the last half of December 2019. Almost immediately, as observatories around the world tracked its path, orbital calculations revealed something stunning. The path Atlas was taking was a near-perfect match for another famous visitor, the Great Comet of 1844. German astronomer Mike Meyer ran the numbers. The orbital elements were the smoking gun, an inclination of 45.3 degrees, meaning its path was steeply tilted relative to the plane of the planets, a perihelion, or closest approach to the Sun, of just 0.25 astronomical units inside the orbit of Mercury. These numbers were virtually identical to the comet from over a century and a half ago. This was no coincidence. It meant they were siblings. They were fragments of a much larger parent body that had likely split apart sometime in the distant past, perhaps 5,000 years ago, far out in the cold. The cause of that original breakup is a mystery, but the low spin of Atlas is a clue. A violent collision would have sent fragments spinning wildly. This suggests a gentle separation, perhaps from the tidal stress of a distant past by another star, or simply from its own internal pressures building over millennia. It was born from a quiet divorce, not a violent impact. And here was the strange part. Its sibling, the comet of 1844, survived its journey. It became a brilliant naked-eye object and then returned to the outer darkness. Why did one brother live and the other die? Perhaps the original body was not uniform. Perhaps the 1844 fragment was a denser, more consolidated piece, while Atlas was a fluffier, more fragile section. This wasn't just a comet, this was a piece of a celestial crime scene, and it was returning to the sun's glare. And it started brightening, fast. Predictions put its peak brightness at a magnitude of 1 or 2, as bright as the stars of the Big Dipper. Everyone was watching. If you value documented space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and studies published in Astrophysical Journal Letters. Now back to the story. The first clue that Atlas was different, that its brilliant performance was a facade, came in early April 2020. While the world was watching its brightness, a handful of scientists were watching its pulse. They were studying its light curve, the subtle rhythmic variation in its magnitude. A comet's nucleus is an irregular chunk of ice and rock. As it's heated by the sun, jets of gas and dust erupt from active regions on its surface in a process called sublimation, ice turning directly into gas. These jets can act like tiny rocket thrusters, creating non-gravitational forces that can alter a comet's path and even change its spin. But the jets on Atlas seem to have little effect on its rotation. As this lumpy, gassy potato tumbles through space, the amount of sunlight reflected from it changes. More jets facing us means more brightness. More dark and inactive terrain means less. By measuring these tiny changes over hours and nights, you can deduce its spin. A team led by astronomer Kwanji Yes at the University of Maryland used data from multiple observatories, including the Zwicky Transient Facility in California, to pin down its rhythm. The comet was turning on its axis once every 16 hours. For a body being sandblasted by solar radiation and gravitational stress, this is incredibly slow. A slow, steady waltz in the middle of a hurricane. Compare that to other comets. Halley's comet has a complex, chaotic tumble. Comet 67P Churyumov, Gerasimenko, spins once every 12.4 hours, and that spin is thought to have accelerated over time. Many smaller comets spin so fast, in 4 or 5 hours, that the centrifugal force at their equator is a major factor holding them together, or tearing them apart. But Atlas felt almost no such rotational stress. A 16-hour spin is gentle. It's leisurely. It suggested the nucleus was either incredibly solid, or that it had never been subjected to the kinds of violent encounters that would speed up its rotation. It was an old soul. It was calm, but it was already a dead comet walking. Then, the show ended before it began. The frantic brightening peaked in March, and then stalled. Around April 2nd of 2020, amateur astronomers, the sentinels of the night sky, started reporting that something was wrong. Jose de Queiroz in Brazil noted the core was no longer sharp and stellar. It looked fuzzy and elongated. The beautiful green glow of its coma, a signature of diatomic carbon being excited by solar ultraviolet radiation, began to fade, replaced by the pale, reflected light of a growing dust cloud. The engine was shutting down. To get a closer look, astronomers turned to the best eye we have. They got emergency director's discretionary time on the Hubble Space Telescope. Using its Wide Field Camera 3, Hubble turned its gaze to the dying comet. The images it sent back on April 20th and 23rd were unmistakable. Clinical, cold, instead of one solid body. There were dozens of glittering fragments, each estimated to be the size of a large house, scattered over a distance of thousands of kilometers. They were all shrouded in the gossamer veil of a shared dust cloud. Hubble's resolution, sharp enough to see a firefly from 1,000 kilometers away, cut through the haze. It saw not one, but 2 distinct clusters of fragments, evidence of 2 separate disintegration events just days apart. It could measure their distance and speed. One major fragment was 3,380 kilometers away from another piece, both moving in parallel along the same orbital track. They weren't flying apart violently. They were just drifting. The speed of their separation was just a few meters per second. The speed of a slow walk. This wasn't an explosion. It wasn't a collision. It was a crumbling, a quiet, graceful dissolution, like a sugar cube dissolving in water. Why would a comet with such a slow, stable rotation suddenly fall apart so completely? The answer wasn't in the spin, but in the substance. The slow rotation was a clue to its origin, not a measure of its present strength. The leading theory is that Atlas was what astronomers call a dynamically new comet, making its very first trip into the inner solar system. Its body was pristine, a fluffy aggregate of ice and dust with the density of packed snow, never before tempered by the sun's heat, and it was full of super volatile ices. We think of comets as dirty snowballs, water ice, but comets from the deep freeze of the Oort cloud contain much more delicate stuff: frozen carbon monoxide, frozen methane, frozen nitrogen. These substances turn to gas at incredibly low temperatures. As Atlas journeyed inward for the first time in 4.5 billion years, its core was getting warm. Once it crossed the orbit of Mars, the sunlight was intense enough to start boiling these supervolatiles, not just on the surface, but deep inside the nucleus. Pockets of gas built up pressure within the fragile, porous structure of the nucleus. At the same time, the sun's gravity was pulling on it, creating tidal stress, stretching the nucleus by pulling more strongly on the near side than the far side. It was being pushed apart from the inside and pulled apart from the outside. The comet's slow spin couldn't save it. The forces tearing it apart were chemical and gravitational, not mechanical. It was doomed by its own purity. This fate is common for first-time visitors. Comet Ison in 2013 was another comet of the century that brightened spectacularly before disintegrating as it rounded the sun. Atlas was following a known script. Its pristine nature was its death sentence. The 16-hour spin was a fingerprint of a gentle birth. Long ago and far away, a birth that left it unprepared for the harsh reality of the inner solar system. If you value documented space science like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the European Southern Observatory and observations by the Hubble Space Telescope science team. Now back to the story. This model of internal combustion and tidal stress explains the timeline perfectly. The comet survived its multi-million-year journey from the Oort cloud because it was in a deep freeze, but its inbound trajectory was its first and final test. The breakup around early April was a cascade failure. A fracture opened, exposing fresh ice to sunlight. That ice sublimated violently, widening the crack and breaking off a piece. This exposed more fresh ice, leading to another breakup. Each fragment became a tiny ghost of the original, a miniature comet with its own coma and its own tail, continuing along the exact same orbital path. This created a river of debris, a ghost stream that will orbit the sun for millennia. Will it ever create a meteor shower for Earth? Unlikely. The comet's steep 45-degree inclination means its path doesn't intersect Earth's orbit. It is a celestial funeral procession that we will only ever see from a distance. The fragments themselves, most no larger than a building, are now on that same 5,000-year orbit. They are so small, they will likely sublimate into nothing on their next pass, if they haven't already vanished into a diffuse cloud of dust. The data from its death became a cosmic autopsy. Multiple observatories were watching. The Neil Gehrels Swift Observatory used its ultraviolet telescope to measure water production. Before the breakup, Atlas was shedding water at a rate of dozens of kilograms per second. After the breakup, that rate plummeted, confirming the main engines of sublimation had been destroyed. Ground-based telescopes in Arizona focused on the dust, measuring its color and production rate, which spiked as the nucleus crumbled, and then faded as the fragments dispersed. The complex, feathery patterns of the dust tail allowed astronomers to model the breakup, pinpointing the dates and the energy of each fragmentation event using spectroscopy. Scientists could identify the molecules in the gas. They found the expected cyanide and diatomic carbon. The ratios of these molecules confirmed its origin in the coldest, most distant reaches of the solar system. The disintegration, while a disappointment for stargazers, was a scientific windfall. It was like a controlled demolition in space, giving an unobstructed view of a comet's primordial interior. We got to see the ingredient list of the early solar system. This is cosmic archaeology. By studying the guts of Atlas, we learn about the chemical conditions that exist before the planets were even formed. Its legacy is now written in scientific papers, refining our models of how comets are built and how they die. The story of Atlas became a cautionary tale. Dynamically, new comets are notorious for this behavior. They brighten incredibly fast as their surface layers of supervolatile frost burn off, but this is a flash fire, not a steady furnace. It's a lesson that was learned with the Great Comet of 1577 Zerkpowers, with Comet Kohoutek in 1973, and with Comet Ison in 2013. We were not seeing a strong, active comet in March 2020. We were seeing the last brilliant gasp of a dying one. The slow spin was a red herring. It spoke of a quiet past. But it couldn't predict its violent future. It was the calm, steady ticking of a bomb. The final observation from Hubble, taken weeks after the initial breakup, delivered the most profound insight. Even after the comet shattered into at least 30 distinct pieces, astronomers kept watching. They had a unique opportunity. They didn't just track the fragments' positions. They measured their light curves. They measured their spin. What did they find? Did the breakup send the pieces tumbling wildly through space, like debris from an explosion? No. They found that the fragments were also spinning slowly, very slowly, with periods of many hours, all consistent with the original 16-hour rotation of the parent body. The stability wasn't a fluke. It wasn't the property of a single monolithic object. It was a family trait. The entire primordial body, the one that broke up centuries ago to create both Atlas and the Great Comet of 1844, must have been an incredibly slow, gentle spinner. The fragments didn't just carry its orbit, they carried its memory, its very rhythm. This reframes the entire picture. It suggests the original object may not have been a single body at all, but perhaps a contact binary, two smaller comets gently touching, or a very loosely bound system. The breakup wasn't the creation of fragments from a whole. It was merely the separation of pre-existing, slow-spinning components that had been traveling together for billions of years. The 16-hour spin wasn't just a clock. It was the shared, steady heartbeat of a family of objects, a heartbeat that was preserved for eons, right up until the moment they finally drifted apart. A slow spin, born from a quiet breakup, billions of miles away and centuries ago. It was a clock, ticking steadily for 4.5 billion years, right up to the moment it fell apart.